Good afternoon.
Good afternoon.
Uh, I have got queries regarding last class.
Yes.
One, uh, we are finding the derivative to find out the pressure in
Okay.
one of our first problem of the last class.
1 minute. Let me open.
Yeah. Average pressure.
Yeah. In last class, right?
Yes, yes, yes.
Last class. What was the question number?
Question number one.
Okay.
The
Okay.
partition
Yes.
function
Yes.
was
Yes.
given.
Yes. I got it. Now
Uh,
ask.
yeah, and so we need to find the derivative with respect to v, ln q, with respect
Hmm.
to v,
Hmm.
and if we differentiate with respect to v, 3 will come, 3v square.
Hmm. Okay. Yes. Yes. It's v cube. So yes, 3 will be there. Yes, you are correct.
And that's why the average g will
G
also
will
not
also
become
be there.
zero.
Okay. So okay. So let me do one thing. Let me again discuss this thing because this is a wrong thing I have done in the last class probably. If anybody joins, then I will discuss it again. Okay.
Okay, right.
Okay. So it's already 4. So let me share my screen. So is it visible?
Yes.
Oh.
Yes.
Okay. So last class there was a mistake actually while calculating this average pressure. We have to take that derivative with respect to volume. So eventually here this is a v cube term, so it will be 3v square. Okay, so 3 will come. Let me write in a different color. This was a mistake. 3 should be there. So if 3 is there, so where the pressure is used, let here the enthalpy, this will also be changed because average energy is okay. Average energy was this is correct, but here obviously there will be another 3 term due to average pressure. 3 will be there. So now if you add it, then it will be eventually 3 plus 3 by 2, so it should be 9 by 2. Okay, so there was a mistake. And also if h is changing, h is 9 by 2, so it will be 9 by 2, so it's not 0 even. So it's not in equilibrium in that case. If it is 0, then that means you can consider that equilibrium. But here eventually it is not a equilibrium. It will be 2 kb 3 to the power 5 by 2 a cube v cube. Okay. So there was a mistake. So you should also correct it. Okay. Thank you. Okay. So let me start today's discussion now. Okay. So first question, what we should discuss that in last class I said that we'll discuss that symmetry number in the light of group theory. So let me discuss that symmetry number. So first let me write down the question. Okay, no, first let me discuss symmetry number, then we will discuss. The first question is um, calculate the or what define the symmetry number just and that. Then we'll calculate symmetry number for various type of molecules. Then it will be uh, more clear. Okay, first define the symmetry number. Okay, so what was the formula for our rotational partition function? That was QR was
8 pi square I cavity by
I
sigma h
cavity
square.
cavity by sigma h square. But it's at the higher side of temperature. That means eventually our temperature must be very greater than our rotational characteristic temperature theta. If it is not, then we know that we have to consider that our well-known generalized formula, that is sum over j e to the power minus beta epsilon j, and if there is degeneracy, which is eventually there in case of rotational energy levels, that is 2j plus 1.
GJ.
So then we have to consider this kind of formula, which is called direct summation method. That is already we are familiar with, but when the temperature is very greater than characteristic rotational temperature, then we can directly consider that in pi square I kb this formula. So in this formula, this sigma appears. This sigma is eventually symmetry number, right? Okay. So first, let us consider the very trivial case. This is also discussed in the class also. That for homonuclear or homodiatomic molecule or heteronuclear diatomic molecule, then let's say if you consider HCl, this is a heteronuclear diatomic molecule, right? Heteronuclear diatomic molecule. So in case of HCl, the sigma will be eventually what?
1.
1. So why this is? So let us consider this HCl. So when you rotate it, there must be we are considering rotational partition functions. We have to account the rotation only. So forget about everything. Vibration, translation, not anything we should not consider here. We have to focus only in the rotational part. So if we consider the HCl, let starting from here, HCl, if you give a rotation by 90 degree, let's say, so what will be the structure of HCl now? It will be like this. After giving of rotation 90 degree, it's pi by 2 rotation. Again, it's pi by 2 rotation. Then again, it will be CLH. If you give again pi by 2 rotation, it will be again, sorry, CLH. And after giving another pi by 2 rotation, it will be again in the first form, HCl. So if you see, we have to give the four rotation. After giving 4 rotation, this rotation we are giving around this axis. Sorry, not rotating in. If it this is called for HCl, let me draw it clearly. This thing should be clear. This HCl, this axis is called molecular axis. Okay, this axis is obviously because it is along the molecular bond of the HCl, so it's actually the molecular axis. Or let me draw in a different color, then it will be more visible, I think. Uh, this axis is molecular axis. Should be another one axis. So we are considering the center of symmetry is here, though it should not be there because it's HCl. So it should be towards the Cl molecule, but for sake of our convenience now, right now, we are considering this is there and this should be another axis. So there must be 3 axes, X, Y, Z, or among these, this first axis I have drawn, that is the molecular axis. So you can give 3 types of rotation here. So first, if you rotate through this molecular axis, so it will be rotate just. Let me on my video as well. Then it will be better to explain. Okay. Okay, so am I visible or only the screen is visible?
Both is visible.
Okay, so now in case of molecular axis, let's say this is the HCl molecule and this is the molecular axis. So when you rotating around the molecular axis, it will be just rotating like this. Okay, so now, so just look at carefully when you rotate along this molecule, this axis, no structure is generating. The structure is remain same. HCl, HCl, HCl is same. But when let's say there is one more axis, if you rotate along this axis, the molecule will rotate like this. Okay, or along this axis, then molecule will rotate like this. So both rotation are similar, yeah, equivalent to each other. So you can consider any of the rotation. So here we have drawn that rotation along this axis. So when you rotate it, first it's HCl, this is HCl, then if you rotate, so HCl again rotate. So there will be this kind of rotation. Okay, around this axis. Okay, so there will be four structure will be generated. So you see, all structures are different. Now, but instead of HCl, if you consider a H2 molecule, H2 is eventually a homonuclear diatomic molecule, right? So, in case of H2, if you rotate it similarly, then what structures will be generated? First, it's H2. After giving a rotation of 90 degree, it will be H2. Again, if you rotate, so same structure generated. You have given just 180-degree rotation, not a total 360-degree rotation. After giving 360 rotation, the structure should be same. But if here you see, so when you rotate 360-degree, eventually there one structure is already generated. The same structure has been generated after giving 180-degree rotation. So 360-degree rotation is not needed here. That's why this term will be very clear when I discuss in terms of group theory. But first, understand this thing. So it will be just 180-degree rotation is needed instead of 360 degrees. So you can think of it's just 360 by 180. So this number is n if you consider n. So n here is 2. So 180 instead of 180, if just 90 degree of rotation is needed, just I'm saying, so then n should be the 4. So in this way you can calculate that number. So this number here you can understand this is direct to the symmetry number. That's why that sigma is 2 in this case. But by rotating this molecule again and again, you can calculate the symmetry number. This is the original definition of symmetry number. Why the symmetry number is coming here? This is due to this rotational axis. Due to if you give the 180 degree rotation, you can obtain the same result which you should obtain after giving a total 360 degree rotation. That's why this n is 2 here. So in case of benzene, you can see, just I'm saying, in case of benzene, if you give the 60 degree of rotation, you will have the same. Or in case of BF3, in case of BF3, if you rotate just by
120 degree.
120 degree, yes, so then it will be 3. So in that way, you can calculate the symmetry number. But this is not very trivial for difficult types of molecule. So that's why there is a formula kind of thing you can say. Just you calculate the point group of that molecule and you evaluate the order. If you know point group, then it's directly written over there in the list what is the order of the molecule. You don't need to calculate even. So you know order of the molecule, just divided it by 2, you will get the symmetry number. So this is the direct formula type. But the original procedure is original definition of symmetry number is coming with this rotation. So you can calculate. Just let us calculate. So here it should be. So here it is sigma is 2. Sorry, 1, and here it is sigma should be 2. So so it's clear. But let's say we should consider a different type of. So what definition we have considered here? There are sigma. Let me write it the definition. Sigma you can calculate order of the point group uh, divided by 2. So this should be the sigma. So we have to calculate the order of the point group, but so do you know the point group, or I should explain?
A little bit.
Please explain.
Okay. So I'm not going very in details, but because it's a different course, so just I'm discussing very in the surface level. I discuss. So first, consider this a common molecule. Let us consider H2O, water. So water is okay. So this is our water molecule. So in this case, in this water molecule, if you just try to find out the symmetry number, if you try it, so then there will be, you have to find out the axis, the center of mass will be there. So one axis will be in this direction,
C2.
another sigma will be 2. Sigma will be 2, but let us discuss. Just let when you rotate it. So first we have to identify the point in symmetry elements. What are the symmetry elements? There are rotational symmetry element, there are reflection type of symmetry element. These symmetry elements are there. Okay. So just considering first, not H2. H2 is a difficult. BF3. BF3 is a planar molecule, you know. So what this Cn is the rotational symmetry. Cn is called the, I'm not discussing details, just understanding rotational symmetry. How you can evaluate this rotational symmetry? Just you have to find out the n. What will be the n here? Just I have discussed. Just
3.
3, because here you can see after giving the rotation 120 degree, you will get the same structure. Okay, so that means n should be always 360 degree divided by theta. Theta means that angle by which you are getting the same molecule. Here it is 120, so here should be theta degree. So it's 360 degree by 120 degree, so it is 3. Okay. So similarly, if you consider benzene, then it will be 60. Theta should be 60 for benzene. So theta should be 60 degree. So then n you can calculate, it should be 360 by 60. It is 6. So you can say here C, the symmetry element is C3. Here it is C4. This is C6, sorry, rotational symmetry. These are only the rotational symmetry, but there are also other kind of symmetries as well. Reflection symmetry is there. Just you can consider this molecule BF3. Just first we complete this discussion. BF3. So how you can evaluate the point group I'm saying? So here you can see, if you pass a plane here, mirror, then these total parts are symmetrical. Both sides, it will reflect to each other. So that this is called a plane of symmetry. Sigma. You have already listened this terms probably, plane of symmetry. So plane of symmetry is there. So how many plane of symmetries are there? One is in this direction,
2.
in this way,
Sorry,
and
4.
in this way. Three plane of symmetry you will get here.
Molecular plane.
Molecular plane of symmetry, a molecular plane, but this should be said that plane of symmetry, because around this plane you are getting a symmetry operation. Just if you draw it like this, so when you pass a plane in this way, so you see overall molecule reflect to each other. So there is a sigma. This sigma should not be confused with the symmetry number. This sigma is the symmetry, plane of symmetry, sigma. So you will have the 3 sigma. But there are two kinds of sigma. If you remember, what was our symmetry axis? The symmetry axis should be in this way, perpendicular to this plane. You are rotating rotating the molecule, but around which axis, that you have to find out now. So that axis should be in this way. Means if this is your molecular plane, here is your BF3, you are rotating around this axis like this, 120 degree. When you rotate 120 degree, you will get it. So you see, this is our symmetry axis Cn, and the plane of symmetries are like this, in this way. You have studied organic chemistry, so you can see this molecular is actually in this direction, this Cn, and the plane of symmetries are like this. So these plane of symmetries are containing the molecular axis. So group theory is totally, you have to visualize it. Okay, I can say it, but you have to visualize. When you passing that plane, that should contain. You have to check whether this is containing the molecular axis or not. If this plane of symmetry is containing molecular axis, then this should be sigma v.
V.
Okay. Yes, sigma v. So here should be 3 sigma v. And also you can give a plane of you can give also a symmetry operation just along the plane of that molecule. In this direction there is a symmetry axis, the rotational axis of symmetry. You are sigma v's are 3 sigma v's in this direction, and also you can also have a symmetry, plane of symmetry along the plane of the molecule which is perpendicular to the molecular axis. This is called principal axis. Okay, here this is the principal axis. There may be other type of Cn as well. Here we have get C3, here may be C2. This C2 is also here. Just look at it. In the
3C2.
3C2 will be there. How? If you rotate along this axis, then also you will have a rotational symmetry. But this is C2 because you are rotating 180 degree. Which is the largest number here? 3 is the largest number. So that should be the principal axis. And this C2, 3C2 along these 3 direction, this 3C2 should be our 3. This is not principal, secondary axis. Okay. So here we have obtained 1 C3, 3 C2, and 3 sigma V and 1 sigma H. This is called, which is perpendicular that principal axis, that is called sigma H. So these are our symmetry operations here. So how we can obtain the total symmetry operation? First you have to consider C3. So if you have C3, then you will have C3, C32, C33. This you have to understand. This is called our cyclic group. Okay, that you should not understand, but just you have C3 because you are rotating 120 degree, but you can give another 120 degree rotation by which you can get the same molecule. So that is C3 twice. Again, you give the 180, 120 degree rotation, you will have the C3 same molecule. So it is C33. So eventually C33 is E. What is E? E is any operation that is
Identity element.
360 degree, yes, or twice of symmetry element. It's called identity operation or identity element. Element is because it's an element of group, that's why it's identity element or identity operation here you should have. So this operation you have get okay, again that there was 3C2. So here also you have considered that C2 and C22. So C22 again is E. So you will get 3C2 here. Sigma V. Sigma V, sigma V square. Sigma V square will be again E because you are giving reflection once. Again you reflect it. Then again it will be same. Just sigma V. Again sigma V. So you are getting the same thing. So sigma V is again E for sigma H also. For any sigma, if you give it twice, it will give the E. So what is the total operation you get for this BF3? You have C3, C3 square, E. You should write the E first, E, because E will be always there. If anything is not there, but E should be there. So E is C3, C3 square, 3 sigma V, sigma H, and 3 C2. So these are the symmetry elements. Symmetry elements present in this molecule BF3. So what will be the point group? You have to consider that first principal operation, that is C3, and you have to consider now what should be the point group, C3V or C3H.
D3D.
Oh, no, that I'm coming. Okay, C3 first you have to do step by step. C3 is there, so I have write it C3. So now you are looking at here is V, here is H. So when V and H both are there, what you have to consider? H.
V.
H, not V, H. H should be considered. So here you have to consider H, sigma H. And here is 3C2. When both C3 and C2 both are present, means you have another secondary axis of rotation. Instead of C, you have to write D. Okay, so it will be D3H. Okay, so D3H is the point group of BF3. It's clear. It's just nomenclature, but you have to
Yes.
when when this is known to you that D3H is the point group, how you can how you can obtain the symmetry element from here. You can see here it is D3, that the C3 should be there and C2 should be there. That's why it is D, and sigma I should be there. By this you can evaluate the all operation. How? First C3. So if you have C3, that means you have C3, C32 and C33, which is E. Then add C2 all of them. So first C3, C32, E are there. Then add all of them C3, C2, then C32, C2, then C2. So these all three will be giving the same C2. So this will belong to the same class. I'm not going into that details. All these are not different. So that's why we can write it as 3C2. So again, after having it, you have to add it with sigma H. So when you add it, so we have all these things already, C3, C32, 3C2. And when you add it with sigma H, you will have C3 sigma H, then C3 2 sigma H, then again sigma H, then 3C2 into sigma H. So these things you will obtain. So I'm not going into details. Here, this will give you the sigma V, and these things also will be there. So by this procedure, because group theory is a very long thing, I'm not doing all these things, but by this procedure, you can obtain the symmetry elements present in the point group. So what is important here, when you have this point group, you should understand, you should evaluate the number of elements present in the point group. Or if you have the molecule, first you have to identify the point group. So this will be very useful when you study the group theory. And this is a statistical mechanics course. The statistical mechanics course is usually in the it's coming after the lesson of group theory. That's why I'm saying. Okay, but it's not very important. It's that much. But let me calculate that molecules what we have done already. Few molecules. Let us calculate. Then it's okay. Just let us consider the molecule H2. What will be point group for H2? Or before H2, HCl, that we have called calculated already. What is the point group for HCl?
CS,
CS. In CS, what are the elements? CS, E
C1.
and E and sigma V, right? In CS.
Yes, yes, sorry.
No, CS is not. Here you have the rotational axis. Three rotational axis I have drawn, right. So in this direction, there is no symmetry because the structure is not repeating. But being that axis, molecular axis, when you giving the rotation, you can have the HCl again and again.
C
Okay,
infinity.
C infinity, yes. So C infinity is there. So this is our the principal axis, C infinity. Or um, after C infinity, E is there. Any molecule E should be there. That is trivial.
Molecular plane.
Yes, molecular plane along this, containing the molecular axis. Along this direction, molecular plane will be there. So it should be
Sigma H.
sigma H or V.
H because it contains that. Sorry, V.
Sigma V. Okay. Mm, I 1 minute. Sigma V is there. H is there. No, no, no sigma V is there. Sorry. E and C infinity. How sigma V is there? This is HCl molecule. You have to consider these axes, right? How in this direction there is no molecules are there. You can't cut the molecule even. This is the HCl. In this is the molecular axis, right? You are rotating. You are rotating in this way.
Yes.
So if you apply the plane in this way, then it will contain the molecular axis. Or
Yes,
it,
I am telling that.
yes. So here the molecular axis is not, sorry, molecular plane is not there as well. Okay. So only two. So in case of this type of homonuclear diatomic, heteronuclear diatomic molecule, there are only two elements, C infinity and E. Okay. Is there any other? So what should be the point group? Point group, it's C infinity V, right? Yes. C infinity V. Hmm. So it is called C infinity V. So and what should be the sigma? Or what is the G here? The order of group is 2. So sigma should be 1. Okay. Why it is C infinity V? Because there is no V, but we have written here V, right? Why?
Yes,
Because this we have to identify the rotational axis, right? That's why I have written the V. This is the HCl molecule, so you have to just I have to let me do this H2. It will be clear. So you see here, in case of H2, there is a plane. In this way, there would be a plane. Plane of symmetry will be there. So here, C infinity is there as it is. E was there. This sigma is there. This sigma is also containing the, you see, this is the molecular plane, and here also one axis is there. So C2 is there and sigma is there. So C2 is there and sigma is there. Okay. So what sigma it should be? It is all, if you consider this H2 molecule, this is the C infinity, and here also, because it's H2, you can rotate it like this. So here it will be C2. C2 is there. So, and in this direction, you can have the plane. So it should be, it is intersecting a perpendicular the axis, so it is sigma H. So that's why it is our D infinity H. It's called now it will be D infinity H. So make the differentiate from this. That's why we have applied V here. Okay, that is the reason. So here the order of group is 4. So sigma will be 2. So in this way you can do, or otherwise I have told you earlier that you can have that rotational axis. This is the rotational axis C2. Why it is not correct? Because you can see for H2 molecule the primary principal axis is C infinity, not the C2. Okay, so that's why it's not very much correct. You have to consider the total point group, then it will be correct, because C infinity is always there. So in this way, you can calculate few others molecule. Let me do it. You can do, okay, benzene. What is the point group for benzene? Just we can do it in just, we have to not consider all the things. Let's see, E is there, C6 will be there. So if C6 is there, then obviously C2 are also there. C2 will be there. Sigma will be there. Sigma V, sigma E, both will be there. From here, you can calculate it will be D6H. Just similar to BF3. In BF3, all other things are there. In also this benzene, other operation you can also have generated. This is not only these things, other operations are also there. So D6H, and for D6H, the point group, the symmetry elements are 24. So sigma will be 12. Okay. One of the famous molecule is CH4. This belongs to tetrahedral point group. The point group is tetrahedral, and the elements of tetrahedral point group is same as the D6H. So it is 24 and sigma will be 12. Okay. First, after CH4, if you consider another molecule, let's say octahedral molecule, any octahedral molecule, just like SF6. This is point group is octahedral. That's why it's octahedral molecule. Uh, and what is the number of symmetry elements here? I think 48. What is the yes, 48. It will be 24. So from if you have any group theory book, you can check the symmetry elements, or you can calculate even when studying group theory. You can calculate the tetrahedral, octahedral point group symmetry elements. Okay. Any other molecule there? So in this way, you can calculate it. Okay. So, but in our course, basically, we have to only focus this. I have written these molecules. Either it is homonuclear, heteronuclear, then you can easily calculate it. If it is homonuclear diatomic molecule, sigma will be 2. If it is a heteronuclear diatomic molecule, sigma will be 1. Or if you have tetrahedral, 12, octahedral, 24. Other things, it's not very much important. That does not. Okay. Okay, so if you have any doubt regarding this symmetry element, you can ask me. Then we'll move to the next question. Because this is a group theory part. Okay, I can't explain all the group theory things. Then it will be a course, another new course.
The whole group theory is needed for that.
Because you have to first understand the elements. Otherwise, how you can explain? Because I did not written here for benzene. There will be S, improper axis of symmetry. These things will be there. Why I have considered all these C2 as the same 3C2? For that, you have to understand the class. First, you have to understand the what is the group. Group is a mathematical term. Any set, you can think of any set that can form a group. For that, that group's elements should follow some specific property. That there must be an inverse element, there must be a identity element. These things should be there, by which you can say a set as a group. You have studied probably field, ring, group, these things, right? For any
Yes,
say, up for certain condition, it will be ring. After certain condition, field, then it groups appear. So before that, you have to understand that group in a mathematical perspective. Then you have to
both are
understand this.
same.
Huh?
I have studied the mathematical group theory. Both are same.
Yes. What? No. Otherwise, why it is called group theory? Because these elements, symmetry elements, you obtained here, these forms a group.
Then quasar, associate, all are maintained.
Exactly, all are maintained, obviously. Otherwise, how you can inverse element is there for every element? These are the inverse element. If for each element there will be inverse element. For C3, this is inverse. For sigma is a self inverse. C2 is also self inverse. Sigma V self inverse. Identity element is there. Associate rule will be followed. Everything will. That's why it's called a group. Otherwise, why it should be a call? You will call this a group. Okay, so that you have to
Okay.
understand. Then why I have written this all as 3 sigma v? You should write it sigma v 1, 2, 3, because these all sigma v are same. Same means belongs to same class. Same class means there must be an operation which makes it a same class. That is here a C3. I'm not going. Then you see, I can write it here 2C3. I have not written it because you can't write it. Both C3 are not belongs to same class, but all C2 belongs to same class, or sigma v belongs to same class. These things. So group theory is very, very interesting thing. This is only the point group. After that, when you go to point group to solid state group, that is way more interesting, because this it's only a one, you can think one dimensional thing, right? Because we are considering molecule. When you consider solid state thing, that is a three-dimensional stuff. So there will that SU, SO, SO2, these types of group will be there. This is way more difficult, but the point group, for in chemistry we have just point group. In condensed matter, in physics, these solid state groups are also be taught. But still, these point groups are coming from that mathematics. The idea is from mathematics. Okay. Okay, so we should not discuss these things very detail, because this is a separate course. You can check some videos if you want to learn this group theory. Point group is very trivial, not trivial. Saying you can learn point group in your course. In BSc, not BSc, in MSc, there must be in details. In BSc, you will have only the knowledge of the symmetry operation, these things. But this formation of groups, or there is a great orthogonality theorem, there is mathematics will be there, right? Here you are seeing just the operation. but there are very rules are there from a molecule, which modes are contributing to which vibration, which rotation, that you can evaluate. And from there, you can also say which molecule will be vibrationally active, IR active, Raman active. These things you can also say. So this will be that's why group theory is very, very important. Group theory is a tool which essentially reduce your work is a huge amount. If you identify the symmetry elements, you can classify a group, classify a molecule. So from that, it's very effective. So that's why you should study group theory very well. It will give a wow like experience. Okay. Okay. So it's enough. Now let us go to the next question. Group theory is okay. Okay, so let me open the question number. Okay, let me open it. Okay, one second. Okay, so today we will discuss some questions from the rotational and vibrational partition functions. So that as we have discussed, so let me open it first. Okay, so question number two. What is the okay. Before that, I should discuss these because for these we need 1 minute, please. Uh, Okay, because I have said in one class that CP minus CV. So CP, what is the relation between CP and CP? CP minus CV from our
NR,
class. Yes, NR. That is for
ideal gas.
what is the general relation? That is we forget always. I also forget. That's why I thought we should do it. It is very important. Always NR is not correct. So that CP minus CV is this is the general relation. It's valid for all gases. So how you can prove it? It is from a pure classical thermodynamics. It's not a statistical thermodynamics, but that we have to do it. One another form is there. This is one form. Okay. Another form is that Cp minus Cv is del V, del Tp, del U, del Vt plus P.
Yes,
From this form, we can evaluate that form. So first we have to. So how you can do it? What is C? What is Cp?
del H del T at constant P.
Okay. Before that, this, and we know del QP is eventually a del HP. This is CP. And CB is
Del U del T
sorry,
at constant V.
D cross Q you should write. It's not a state function. Okay. And H is equal to
U plus PV.
U plus PV. So let me write it U plus PV. Okay. So this we have then CP minus CV will be This we have to calculate. This part is there, okay. So how you can calculate this lesson? Do you have any idea?
From first law,
First law. Okay, let us check. U is a function of
volume and temperature.
volume and temperature. So you can write it. If du equals to del u del Vt dv. This is Euler's exact differential formula. Del u del dv dt. So du will be del u del Vt dv plus cv dt. This formula we used often, very often. So from here you can write it. Now take the derivative with respect to temperature, but at a constant pressure. So we are taking du if it is constant pressure. So what will be from here? It is just cv, and it will be del u del Vt del v del t p. Okay, so this is clear. Just we have to now put it here. So Cp minus Cv, that will be, you have to take the difference between this. Okay, okay, okay. This is eventually Cv. Okay, let me write Cv, right? And what was the Cv? Cv was clear. Del u del t
Del u del t at constant v.
v. So just that means del u del t p minus del u del t v is eventually this. Del u del Vt into del v del t p. So we have obtained, hence Cp minus Cv. Just we have to insert this result here. So write it. So del u del Vt del v del t p, and plus there was another term, that is p del v del t p. Just now you take common del v del t p, you will have del u del Vt plus p. So this is the formula. This is one of the formula. Okay. So we can check for ideal gas. For ideal gas, this will be 0.
Yes.
And this part del v del T p, PV equal to nRT. So del v del Tp. So from here v is equal to nRT by P. So it is nR by
P.
P. So Cp minus Cv equals to nR by P into 0 plus P. It is n. So we just remember this. Eventually we have to remind this thing. And it's not your case. I also always forget this formula.
This
That's
is for
why
all case.
this is general formula.
Real gas, van der Waals gas.
For everything you can do it. Always you have to remind this formula. So that's why in exam I have derived this formula because I forget it. But I know this is not general formula in R. It was needed to solve that question. That's why I have to derive it. Then I can use it. Otherwise, so it's better to remind, but it's okay. Okay. So now what we have to prove? We have to prove this formula. How you can do it? We have this. from here we have to derive this.
PV equal to NRT.
No, that's also ideal gas case. It's general formula. For that we need, you can see here, del V del Tp is there. What is not there? Du dVt is not there. So we have
Yes.
to use a form of du dVt. So again, we know del u del Vt. What is this term? What is this?
CV.
No, no, no. This is pi T internal pressure. So this is internal pressure and this is equals to T into this formula you have to remind. This is thermodynamic equation of state. There are two thermodynamics equation of state. This is one of that. One is internal pressure, another one was internal volume. This is del U del BT. Another one is, I think, if I'm not wrong, the formula was del H del PT, del H del PT, and this was volume. So it was V minus, I think, T into del V del 2T. Yes. These two were the thermodynamic equation of state. So this you have to remind. This is very useful, very useful, because from this thermodynamics equation of state, you can have a question from CSI, NET or GATE. Regularly you can have you have questions. Okay, so now just you insert it. You have to insert this del U del V T plus P. So del U del VT plus P equals to T into del P del T V. Just write it there so you can have Cp minus Cv del V del T del V del T T into del V del. My headphone is connected. Let me connect it again. Okay, okay. So we'll go into next question. Yes, let me have. Okay. Do you know what is the adiabatic index?
No.
You know, but you don't know the term actually. So that's let me write it. Calculate adiabatic index of methane gas at high temperature, very low temperature. Ada adiabatic index You know this thing, but let's say in CSR exam, they ask to calculate adiabatic index. You know, but you don't know the nomenclature. That's why you have to leave the question. So adiabatic index is just gamma, CP by CV. Okay, do you
Oh,
know it?
yes,
Yes,
obviously.
but that term you don't know. If you remember, this gamma appears in the adiabatic process that Pv to the power gamma
PV
equals
to
to
the gamma equals to
constant.
constant.
So that's why it's called adiabatic index. It guides whether the process is an adiabatic process or the isothermal process. So from that definition, it's called adiabatic index. Okay. So now we have to calculate it. Before that, one thing we should discuss between the CP and CV, what should be larger? CP and
CP,
CP. CP is 5.
it is CV plus R.
You are you are talking mathematically, physically.
Heat capacity at constant pressure.
So what?
So volume is not constant. That means there is some work done.
Yes, yes, completely. So CP was we know heat capacity means the amount of heat required to increase the temperature of that macroscopic system by 1 Kelvin, 1 unit. So this is a CP. That means we have to carry out that procedure at constant pressure, and CV, the same definition is same just at constant volume. So now if you have a macroscopic system, macrostate like this, let me write it. So you have to increase the temperature. Let's say uh, at first the temperature was T. T is the temperature of that macroscopic system. Volume is V, and okay, and pressure is P. Pressure, there is a pressure that is P. Okay. So now what will happen? Or you should write it here. That's because these are the state property. We have to give heat d cross q. It's a constant volume process, so there this piston is constant there. The volume should not be changed. Volume will be remain constant. Now you are giving the heat. So from first law of thermodynamics, you know that d cross q is equal to du plus pdv or d cross w.
Yes,
So now the piston is fixed, so d cross w will not be
0.
0, will not be there. So d cross q will be du. What does it mean? Mean that you are giving a heat, and that heat directly increase the internal energy.
Internal energy.
And temperature is, what is the internal energy? You know that E average was kb t square dln q
Del N by del
del
beta.
T. So temperature is directly related to the average of internal energy. So when you are giving the internal energy, you increasing the internal energy, it will directly increase the temperature. So temperature will be increased. So for that, let's say you need a U amount of heat. After giving U amount of heat, volume will remain same. Volume will remain same. Pressure will be increased, and temperature will also be increased. Let's say now it is T plus 1. Then only it is the CV, right? Because we have to increase the temperature by 1 degree. But coming here, it is okay. So now here the volume is not constant. Pressure you have to constant. You have to say, keep constant. So here first it was TVP, same state was there. Same state was there. In both cases, temperature you have to increase by 1 degree. Okay. So now here you are giving same amount of heat. Uh, Not same amount of heat, you are giving heat to increase the temperature. But here you see du plus pdv. Some work done is there because here now the piston is lifting. because that is volume is not fixed. So you have to keep the pressure constant. So volume, piston will be uplifted and the volume will be increased. Now you see you are giving some amount of heat, let's say 10 amount of heat you are giving. Some amount of heat is being used to increase the volume, that means in the mechanical work. Rest of the amount of heat is going to increase the temperature, that means the internal energy. So you see, all amount of heat is not be manifested to use to increase the temperature. So it's clear. So here, to increase the amount of temperature by 1 degree, you require more amount of heat. Okay. So it's clear that D cross Q constant pressure must be greater than D cross Q constant volume. So if it is, so now it's clear. So now you can write it D cross Q. Now T both in both cases, del T at constant pressure is greater than D cross Q at constant volume. So from here you can claim Cp is always greater than Cv. Okay. So this is important. Okay. Now what was our question here? That okay, Cp by Cv is there, and Cp minus Cv also we have in this lesson. We have to calculate that gamma for methane gas for very high and low temperature. Here we have to calculate it from our classical thermodynamics, means equipartition. Equipartition theory you have to calculate. Then you will do it from statistical. Okay. So how you can calculate? You have to first calculate U, because you have to calculate Cp and Cv for gamma. You need Cp and Cv, and Cp Cv you know both are for both cases. So first let us calculate Cv. Cv is del U del Tv, correct? And if you know Cv, you can calculate the Cp. Okay. So for timing, you can consider as a ideal gas, then Cp will be Cv plus Nr. Otherwise, you can have the general formula as well. Okay. So this is important. How you can calculate this? You have to calculate. So from if you calculate it from there are two ways you calculate. First is equipartition theory. This is our classical thermodynamics. And another is which is more general, which is must be more scientifically correct. That is from our statistical thermodynamics, right? That we have already studied. Okay. So first, if you consider it from equipartition, then you how you can calculate methane gas, CH4.
Adding all the degrees of freedom.
Which degrees of freedom will be there?
Translational, rotational,
Hmm. So we have
and
to calculate
vibrational.
E. Yes, you are correct. E will be translational, rotational energy plus vibrational energy. Electronic we are not considering here because electronic motion is not there. Okay. So ET, ER, EV. For ET, these things you know very well. If there is a n number of atoms in a molecule, then there will be total 3n
Three
number
and
of
degrees of freedom.
3n number of degrees of freedom. Okay. So and for if you calculate first electronic for any energy, so it will be number of modes into
Half kT.
no average energy of that mode. Okay, or energy of that mode. This is our general formula. So for ET, what will be the number of mode?
Three.
For three, because it's a non-linear molecule. Uh, for any molecules, not only non-linear, for any molecule, it's three. And average energy of translational mode is half kVt. That you can calculate from Maxwell distribution even. Okay.
This half kT.
Yes. 3 by 2 kVt you did not calculate?
From I calculate from kinetic theory of gases.
Hmm. That kinetic theory of gases, that is Maxwell distribution, right?
Okay, okay. Then
That distribution you started with, this type of distribution, that was Maxwell
yes,
distribution. Okay. So this is 3 by 2 kBT. And also you can calculate from statistical thermodynamics. You have already calculated that QT.
yes,
If you consider this is 3 by 2 kBT. Okay. Rotational.
Can you explain the number of modes?
Yes, number of modes. Okay. For translational, if you take any molecule, any atom, then there will be three directions to move, right? X, Y, and Z. So from there it's coming. Three degrees of freedom. So three number of modes is there.
Okay, okay, thank you.
Okay. So for rotational, now rotational may be linear and non-linear. So first consider linear. In linear, number of modes, here you can see for a linear molecule, for linear
two.
molecule, 2, because this rotation is not important here. Why? These two rotations are important. Why these rotation
This
around
is
this
not
axis
contributing to
contributing to?
different contribution of the molecule, different state.
No, no. If you remember that, you remember that QR, what was QR? 8 pi square I kBT, right? Divided by sigma E
Yes,
square. I was there. What is I? Mu R square.
mu r
What is
square.
this R? This R is the difference with distance between the axis and the molecule. That is 0. For rotation around the axis, if the molecule rotates around its own axis, there is no difference between the molecule and the rotational axis, right? Here it is R.
Yes,
Here it is R, but in that case there is no. That's why QR is 0. Okay, that does not contribute in the energy. So that's why you have to consider it 2 into half kV. But when you calculate it for from our statistical thermodynamics, you will get direct kBT, because from statistical thermodynamics you will calculate energy. So obviously you will get the kBT, not the 2 into half kBT. But for non-linear, it will be 3 into half kBT. So it is 3 by 2 kBT. So this formula you can prove from our statistical thermodynamics when this is already done in class. This can prove only when theta is very, very less than TR. Sorry, temperature must be higher than the rotational temperature, catastatic rotational temperature. Okay, so eventually we are considering that in that temperature already. If it is less than theta R, then the temperature is very less. In that temperature, you can't apply the equipartition theory. Equipartition theory is a classical result. So, and classical result will be very accurate in higher temperature limit. You know these things. In case of lower temperature, you have to consider the statistical thermodynamics. That's why it's very important. And good thing is, any quantum mechanical result, any statistical result will be converged in the higher, with classical result in higher temperature limit. We have studied that heat capacity divide heat capacity. You studied that?
what?
If you calculate that CV, what is the CV? I will come into that. CV will be 3R. That is
Yes,
valid only for high temperature. Okay, I'm coming to that. That is also very important thing. I will come into that. Okay, so this is yeah, and now EV in case of linear molecule, what will be the number of
3n minus
modes?
5.
Yes, because total number of modes are 3n or modes or degree of freedom, whatever you want to say. And for linear, 5 modes are already have been used, so there will be left 3n minus 5. And the energy for each mode is kBT. So this is our 3n minus 5 kBT. In case of non-linear, it will be 3n minus 6 kBT. So these are total equipartition energy. Okay. So what I am saying, mm, yes, for methane gas, right? CH4, n equals to 5. So if n is equal to 5, so, and it's a non-linear molecule, so E translational will be always 3 by 2 kBT. E rotational will be here 3 by 2 kBT. And E vibration, it is non-linear, so 3n minus 6, so it is 9 kBT. So total energy will be 15 kBT, right? No, no, not 15, 3 to 12 kBT. So CV will be del E or del U, whatever you want to write, del E, del T, V. So it is 12 kb. And this is for only one molecule, obviously. So in case of for all molecule, you have to multiply it with the number of molecules, total number of molecules. So it should be, this is for, this is CV, but it's for only one molecule. So we can give a bar here just to distinguish. Now, if you calculate it for 1 mole of molecule, then it will be CVM, you know. So here you have to multiply it with now Na.
Na,
So it is eventually 12
R,
R. Or for any molecule, any number of molecule, it will be CV, then it will be Kb just N. N is total number of molecule. So that you have to find out total number of molecule. Okay. So that is, so, and you know, you can write it as NR, 12 NR. N is the number of mole here. So this is CV and CP. CP will be, just you have to add, from here you
NR,
can write the CPM will be then 13 R, NR, 13 R, and here it will be 13 NR. So let's calculate gamma. Gamma will be Cp by Cv. So it will be 13 by 12. So it is 1.083. Okay. So this is equipartition. From statistical mechanics, you can also do it. But this is valid when the temperature is higher. How much higher? First of all, we have considered that theta is very, very less than T. And also now we have to consider for this validation, you know this. This will only valid when this is also very much higher than theta V. Then only you can apply it, KBT. Otherwise, you have to consider that equipartition, partition function. But if it is, now you know that the theta V is very, very higher considered to the theta R. So the origin total is like this. So this is not always true. So if temperature is very low, then you can't consider these energies, this contribution. This contribution will not be there in that case. So at very low temperature, this contribution will not be there. So now if low temperature, if theta temperature is less than theta V, then what will happen? Then obviously total energy will be just Et plus Er, no contribution from the vibrational. So it will be just 3 kBT. So CV will be 3 kb. So CVM will be 3 R and CPM will be 4 R. It's clear. So it is just 4R. So here gamma will be, 4 by 3, it is 1.33. So eventually these gamma will obtained because the vibrational, this theta v is very higher. So it's general. And again, if the temperature is also less than the theta r, then you have to consider only the translational motion. No other options. Then you will be always T, and then it will be 3 by 2 kBp. And that means CVM will be 3 by 2 R and CPM will be 5 by 2 R, or CV will be 3 by 2 NR and CP will be 5 by 2 NR. So from here, if you calculate gamma, then you will have 5 by 3. So 5 by 3, you can calculate it. So it is 1.66. So you see, if the temperature is decreasing, theta v is constant. So first it is 1.083, then it goes 1.33, now it is 1.66. So if temperature is decreasing, that means if rotational and vibrational levels are only occupied up to ground state, then it will be gamma will also be increased. Okay, so it's clear. Okay, so there is a formula, you can remind it. This generally in questions, now in questions perspective, in the CSI net or gate, is these questions are asked, then when the high temperature is mentioned in the question, the high temperature is mentioned, let me write it. If in the question, in general, I'm saying high temperature is mentioned, that essentially means the temperature is greater than theta v, greater than theta r. Okay, if it is room temperature, then it is greater than theta r. So you have to consider that translation rotational motion, and also you can consider the vibrational motion, but it will be 0.2 kBt. Instead of kBt, it will be 0.2 kBt. It's 80% less. And it is, if it is low temperature, that means T is less than theta r also, then you have to calculate is 0. Okay, so you have to keep in mind that. Oh, sorry, it's in low temperature. That means it less than theta b but greater than theta r. Then it is 0 kBt for vibrational contribution. I'm saying this is for vibrational contribution. And if it is very low temperature, then theta temperature is less than theta r even. Then rotational, vibrational both are 0. So this you have to remember. Okay.
Translational.
Translational will not be there. Translational, for the energy gaps between the translation energy level is very less, so that can be occupied. Now very low
If it is
temperature,
in 0 degree Celsius.
I'm saying that 0 degrees Celsius also the vibration energy level will be occupied. Okay, because translation energy level will be occupied, because if translational energy levels are not occupied, that means all molecules are in the ground state of the translation energy level, right?
Yes.
So Maxwell distribution, there will be no distribution, and that means temperature is T0 Kelvin. Okay.
Okay.
And for gas molecule, you can't go in that up to that. Before that, it will be liquid and or solid. So we are discussing this all things when it is only gaseous. Okay, not just liquid or solid. Okay.
For very low temperature, we need to consider theta, that is a contribution to the rotational part, to be 0.
For rotational, for vibrational, both. If it is very low
Oh,
temperature. Specifically, it is mentioned that if less than theta or a greater than theta, it will be mentioned. If it is not mentioned, if it is not mentioned in general, then you have to consider up to this. This is more general. Very low temperature, that is not very often asked in the question. You can ignore it. So if it is very low temperature, you can ignore the vibrational contribution. In rotational contribution, you have to consider.
In room temperature, there is 0.2 kVt,
That is from vibrational. Rotational is there.
half kVt.
Half kV. Rotational will be there. Okay. So now going to question number. It was question number 3. Okay, question number 4. Okay, from washroom. The force of what is the value of CV of SO3 gas in terms of. So here you can actually check it. So SO3, how does it look?
Non-linear.
Non-linear. So SO3 is essentially looks like this, like BF3. So what should be
Yes.
the point group?
B3H.
B3. So whenever after studying group theory, whenever you have any molecule, you can evaluate the point. Okay. So now, so ET will be obviously 3 by 2 kVt. ER rotational. So it is non-linear molecule. So eventually it will be again 3 by 2 kVt. Now vibrational. Here you have to consider it. What should be there? There is not mentioned anything. So if there is not mentioned anything temperature, then you have to consider it. Okay. So it will be
12
3n.
minus 6 kVt.
N is 4. So it is 3n is 12 minus 6 kVt. So it is 6 kVt. So total E will be 9 kVt.
9 kVt.
That means, so CVM for 1 mole, it will be 9 kb into Na. So it is linear. So it is Cp. Now you can calculate also CPM. It will be 10. Although it's not correct because it's for the ideal gas, but still. So gamma will be 10 by 9. 1.19. Okay, so in this way you can calculate it. Okay. That six. Plus 154. Where is the questions? I have written it. Okay, we got it. It is equal to 5. Hmm. So now, question number 5. This question we have not done, I think. No. Okay. What is the rotational partition function of H2 molecule at 300 Kelvin? Moment of inertia of H2 molecule is 4.59 into 10 to the power minus 47 kg meter square, and oh, that's it. So you want to try it?
Yes.
Try it, then I will. It's straightforward from question formula based question. What is the QT? QR, sorry. 8 pi square.
I kbt by sigma h square.
What is sigma here?
2.
Yes. Or you can write it mu r square kbt, because you know I is equal to mu r square. So now everything is given. Also, it's not needed because I is directly given to you. So sorry. So again, then it is more easier. So so just put it. So it 8 pi square. I is 4.59, 10 to the power minus 47. KB is 1.38, 10 to the power minus
That's 23.
93. Temperature is 302. 6.626 10 to the power minus 34 whole square. So what would it be? 8 pi square, 4.59, 1.38.
17.24.
Let me also check it. I don't know answer. No, it's not matching. Why? 8, 1724 is not coming. 8 pi square into 4.59 into 1.38 into 300 divided by 2 divided by 6.626 square. It is 71708.71 into now powers 47.23. Minus 47 minus 23 plus 68 minus 2. So it is eventually 17.0871. What was your answer?
17.24.
Okay, it's close. Maybe due to calculation error or something. So it will be around the 17. Okay. Okay, now this question have done. I think. Yes, now this is okay. Assuming
1 minute, my head. Thanks. Just take a minute of here if we go convention. Okay. Okay. Assuming H2 and HD molecules having equal bond lengths. What is the ratio of the rotational partition function of these molecules at temperature above 1000 K? Okay. So H2 and HD both have the same bonding. Let us consider. So here the rotational partition function will be QR 8 pi square I for H2. So I H2 KBT divided by sigma H square, and sigma will be 2.
2.
This is for H2. Now sigma R for HD, it will be 8 pi square I HD KBT divided by just H square. Okay. So just now ratio it. So sigma R H2 divided by QR H2 QR HD. So it will be I H2 divided by 2 IHD, if I'm not wrong. Yes. So now it will be mu H2 R square because R same.
3/8.
Okay, let me do it. So it is HD R square again. So R square has to cancel. So it will be mu H2 divided by 2 mu HD. So and mu H2. What is the formula of mu? Mu is our
M1 M2 by M1 plus M2.
reduced mass. Yes, M1 M2. Or you can write it as 1 by mu equals to 1 by M1 plus 1 by M2. Or that means mu equals to M1 M2. So it will be H2. So it will be MH divided by MH plus MH with 2 into MH MD divided by MH plus MD. Okay, so that will be MH by 2. Okay, and it will be 2. So both 2 will be there. So 4 MH MD and it goes up to MH plus MD. Okay, so MH goes away. So it is MH by 4 MD plus 1 by 4. Okay, so just MH by MD that we have to calculate. MH is
1.
not 1. That mistake.
1 by Avogadro number.
Yes, here ratio is there, so it will be cancelled out. But always you have to write it. Okay, so it is 1 by 8 plus 1 by 4. So it is 3 by 8. What was your answer? 3 by 8, right?
Yes.
So it's 3 by 8. So that will be the ratio. Okay. So it was our question number 6.
But the bond distance is not different.
Bond distance usually different, but here for the calculation purpose, they said that you can assume that bonds are equal, but actually the bonds are different. Okay, actually bonds are different.
Okay.
Okay, next question. So number 7. Okay. This question we have done, I think. 1 minute. This question we have done. Yes. Six. Okay. No, this question also we have done in the next class, in the earlier classes. Let me find out some different type of question. This is just formula based question. You can put the values and you will have the answer. So I don't want this type of question. Okay, let us know this question. What is the vibrational contribution to the molar heat capacity of N2 gas at 1000 Kelvin. The vibrational temperature of N2 gas is 3374 Kelvin. Okay. This question I can do. Hmm. There was one more question. Okay, let us do it first, then we'll discuss that question also. Okay, so what will here what should we consider the vibrational contribution to the molar heat capacity. Okay, this contribution we have studied for a particular mode. What should the contribution to the molar heat capacity? So CV, we know the definition of CV. So again, it is this. Sorry for disturbance. Okay, so CV. So what is the definition of CV that we know? We know that that is del E or del U del T V. So we have to calculate that E for the vibrational mode only. That means the vibrational contribution you have to calculate. So this is for only vibration. Then this E also be due to the vibration that we have to calculate. So and what will be that E vibration? We know this is for average from statistical thermodynamics. This is kV T square dln Q, and that Q also due to the
del T
vibration T at constant V. Okay, and you know that QV is equal to
1
N.
by 1 minus
No. That's okay, but for vibrational means you have to consider the molecular partition function. Then only you can incorporate that vibrational part. Okay, so it is you know that Q equal to uh, Q to the Q to the power N. Actually, that means Q equals to Q to the power N. For vibrational, it will be vibrational. That does not matter. So only N will be there. So here it is kb t square.
value of
Then
the small q.
that you have to calculate. That's why it is vibrational. So this qv you needed. So it's clear. So n kbt square. So it as n kbt square. So here we have considered as q to the power n. That means the molecules are distinguishable. Okay. That's why you have otherwise you have to consider that n factorial even. So this is the formula. Now qv. QV vibrational contribution, you know what is the formula? 1 by 1 minus e to the power minus h nu by kBT. This is considering the ground state energy is 0. That means 0 point energy is 0. Or general formula is h nu to h nu by 2 kBT. So in this question we will do both. First let us consider the original formula, then we will do the formula. Okay, and we will check whether it is same or different. So this is our so what will be the ln q? ln e to the power h nu by kbt So you can write it. Okay, so you know this h nu by kb, so theta vibrational is eventually h nu by kb. So you can write it as ln e to the power minus theta by 2t minus ln 1 minus e to the power minus theta by t. So it is minus theta by 2t minus ln 1 minus e to the power theta by t. So this is how. So now we have to take the derivative dl into dt. So here it will be obviously theta by 2t square minus ddt of ln 1 minus e to the power theta by t. Okay, so it is theta by t square. This term you can write it as, let's say this is z, just then it will be ln z into del z del t. Okay, 1 by z, and z was this 1 minus e to the power minus theta by t, and this is del t of 1 minus e to the power minus theta by t. By t, and this is minus e to the power theta by t, so it will be obviously minus theta into, yeah, not minus theta, it will be del t of e to the power minus theta by t, and there will be another minus sign and it will be plus. It will be theta by 2t square, so it is 1 by 1 minus e to the power minus theta by t, and this derivative should be theta e to the power minus theta by t will be there, e to the power minus theta by t, and theta by t square, and one minus sign will also be there. Is it correct? You can also check, okay? Because if there is only plus minus thing is there, then overall answer will be changed. So we have to take this derivative. So e to the theta by t, and
The minus sign,
yes,
minus 1 by t square.
minus will be there. You are taking the derivative of minus theta by
No, no,
t,
CD.
then
Yes, okay.
2 minus will be there, na? So it will be positive. So it is, and write it as theta into e to the power minus theta by t divided by t square into it is theta by 2t square plus theta by t square into e to the power theta by t minus 1. Okay, so this is our dl into dt. So the average internal energy is kb t square dl. So kb t square into this whole term, that is theta by 2t square is theta by t square e to the power minus theta by t, not minus, plus 1. So when you multiply it, you will have kb theta by 2t plus kb theta by e to the power theta by t minus 1. So this is our e. So cv will be del e del t v. So you have to take the derivative. Okay, so first term kb theta is constant, so kb theta is there. kb theta by, and it will be 1 by 2t square, and minus will be there. Okay, so minus will be there, and from second term is plus again. kb theta is constant, and it is del t to e to the power theta by t minus 1. First term is there. First term is minus kb by 2t. If I'm not wrong, first term is this. 1 minute. Oh, no. Here temperature will be there. T square will be cancelled out. Sorry. Sorry. So in the first term there is no temperature. So this is 0. And only from second term we will have the temperature. And that will be del t of 1 by e to the power theta t minus 1. The kb theta, and we have to take the derivative here again. So let's consider this as z. So it will be del again z in 1 by z del z del t. It is kb theta. It is 1 by z square, and del t of z is e to the power theta t minus 1. So it is kb theta. Let me consider z square right now. So it is e to the power theta t. So e to the power theta t means e to the power theta t into theta by t square, but with a minus sign. So it is kb theta e to the power theta t, and then there will be a minus sign because theta 1 by t is there, so obviously, so it is minus theta t square divided by z square. Z square is e to the power theta t minus 1 square. Okay, so you can check it whether anything is wrong. Yes, because there will be another minus sign here because 1 by z, so it is minus 1 by z square. So this minus sign will go right now. So this is formula. So CV is from the vibrational mode contribution. So it is kb theta square e to the power theta by t divided by t square e to the power theta by t minus 1 square. So this is the formula from for CV. Okay, this is the formula
This is statistical definition.
from statistical definition. Again, it is discrete. Oh, what is going on? Don't consider anything. We have started from the partition function, vibrational partition function, and considering the derive this, the CV, vibrational contribution, and this is the answer kbt square kb not t square. And you can also insert the value of theta. Theta was our, okay, let me also do it. Theta is, what was theta? H nu by
Vibrational temperature.
kb. So that you can also put it here. So then it will be cz kb h square nu square e to the power h nu by
Nu by
kbt
kbt.
divided by kb square t square e to the power h nu by kbt minus 1 square. So eventually it will be h nu by h square nu square to the power h nu by kbt. So it's better to keep in the theta form because here nothing will be sorted out. It will be more messy. So it is the formula. So here you can see one thing we can do, that uh, theta by t, yes, this theta by t, you know, this is called phi. Okay, you can, because theta by t is important. We know always we consider theta is greater than theta v or something. So we are considering the ratio phi, that is eventually theta by t. So then you can write it. This is a b phi square e to the power phi divided by e to the power phi minus 1 square. This formula you can also write. Now, what was our question? In question, they have asked for N2 vibrational contribution N2 at 1000 Kelvin, and the rotational temperature is also given. Okay, so now we can do it. So they have said, and theta is also given. Theta is 3374 and temperature is 1000. So it is eventually 3.374. Phi is 3.374. Okay, and if you consider it for molar, then it will be CVM. Then you have to multiply it with Na, and Kb will be converted to R. Okay, so it is R into 3.374 square to the power 3.374 divided by e to the power 3.374 minus 1 square. Okay, so it is, let me do it, 3.374 square into e to the power 3.374. So this is eventually, let me write it, 3.374 square. It is 29.19. And it is 794.96. So this will be now 2.37. It is R into, you can check by your own as well, 418. And what is the unit? No, what is the value of R?
8.314.
8.314 in joule per Kelvin per mole inverse. So it will be 3.4758 joule per Kelvin inverse mole inverse. Okay. So this is our answer. So you can try considering the definition where the ground state energy 0 point energy is 0. Then what will be the difference? If you consider instead of this definition, if you consider, let's say, QV will be 1 by 1 minus e to the power minus 18 by kBT, then obviously this first term will not be there, right? This term,
Yes.
this term will not be there, this term will not be there, this
Theta
term,
by 2t square.
so it will be 0. So when you put it, this first term will not be there, and you see after taking derivative, the first term is not there. So
Yes.
eventually it does not make any difference. If you consider that definition also, that will not create that much difference. No difference even. Okay, so this is our CV. Okay, so if you have any doubt, you can ask me. In the next class, I thought I will discuss some part from grand canonical, because grand canonical will not be covered probably in the course. So if you, as you know, the classic canonical partition function, so grand canonical you can also be understand. It will not that much difficult. It will be just an addition in the canonical partition function. Okay, so in this class, let me stop. If you have any doubt, you can ask me. Okay, so okay, so then first let me stop screen sharing. Then if you have doubt, you can. Okay, So if you don't have any doubt, we'll meet again in the next class. Yes, any doubt?
Which book is prepared for this type of partition function study?
Partition function type of questions. Okay. For statistical
Now, for the
analysis,
conceptualization of the topic also,
what is
to
that?
build up the concept, as well as for the problem solving.
Yes,
Both of the
problem
things.
solving, I don't know actually. I studied from various CSIR problems, previous year question, NET, GATE. From that, I prepare these kind of problems. Uh, you can check. There is a book for course for theory part. You can follow the Mercury book. Theory part is given, or Patria book is also good for this statistical thermodynamics part. But for question, for this numerical question for CSI net get this type of question, you can check the previous year question set out. There is a book for CSI net get. There is lots of questions, similar kind of question you will find out. Okay, in
Okay.
Amazon it is available for CSI net and get previous year question setup. There you will have this kind of CSI net get type of question. There you will have the question, but in that book that is basically theory part.
Only McQuery.
Mercury or Patria you can also check. Agarwala also have a book. That book is also very important. Uh, if I get the PDF, I will upload in the drive. Okay, that Agarwala
Okay,
book.
that will be very good.
That I will upload.
Any lecture?
Lecture. uh, No, for timing it's okay because for BSCMS part it is way enough. It's enough. If you study again for statistical thermodynamics, you can check Balakrishnan lecture. That is non-equilibrium even. For
In YouTube.
yes, for equilibrium statistical thermodynamics, okay, it's sufficient.
Okay. Thank you.
Okay, I will upload that. Okay,
Okay, thank you.
okay. So we'll meet it again next week at 4 p.m. Okay. Okay.
Thank you.